Here is the hook. A normal database is great when you know the exact words you are looking for. But modern AI often needs something stranger. It needs to find the paragraph that means the same thing, the image that feels similar, the support ticket with the same hidden problem, or the product a shopper would recognize even if they describe it badly. That is where vector databases become interesting. In this explainer, we will build the idea step by step. First, what a vector is. Second, why embeddings turn meaning into coordinates. Third, how a vector database searches by similarity instead of exact match. Fourth, what indexing, filtering, and retrieval do in a real AI app. By the end, vector databases should feel less like a buzzword and more like a practical memory system for AI. Start with a daily life analogy. Imagine a huge library where books are not arranged alphabetically. Instead, every book is placed on a giant map of meaning. Mystery novels live near detective stories. Beginner cooking books live near simple meal planning books. A book about marathon training sits closer to sports nutrition than to medieval history. If you walk to one point on the map, nearby shelves contain ideas that feel related, even when the titles use different words. That is the core trick. A vector database stores items in a space where distance represents similarity. It is not asking, did these two pieces of text use the same keyword? It is asking, are they close in meaning? This is why search can understand cheap flights for a family trip and still find budget vacation airfare with kids. Now let us define the main object, a vector. A vector is just a list of numbers. For AI search, those numbers usually come from an embedding model. The embedding model reads text, images, audio, or other content and converts each item into coordinates. One sentence might become hundreds or thousands of numbers. Humans cannot look at those numbers and read the meaning directly, but the geometry is useful. Similar ideas tend to land near each other. Different ideas land farther apart. Think of each dimension as a tiny signal about the content: topic, tone, object, action, intent, domain, and many patterns too subtle to name. The vector database does not create the meaning by itself. The embedding model creates the coordinates. The vector database stores those coordinates and makes them searchable at scale. The search process has 3 important steps. First, you embed the query. If a user asks, how do I reset my password without my old phone? The same embedding model turns that query into a vector. Second, the database compares that query vector against stored vectors. It uses a distance measure, often cosine similarity, dot product, or Euclidean distance. Third, it returns the nearest neighbors, the stored items whose vectors are closest to the query. In a tiny dataset, you could compare the query to every item. In a real system with millions or billions of vectors, that is too slow. So vector databases build indexes. An index is a clever shortcut that lets the system search the neighborhood of likely matches without checking every apartment in the city. Indexing is where vector databases become production infrastructure instead of a science demo. Popular index families organize the vector space in different ways. Some build graph structures, where each vector is connected to nearby vectors, and search walks the graph toward better matches. Some split the space into clusters and check the most promising clusters first. Some compress vectors so more of them fit in memory. The trade-off is usually speed, accuracy, cost, and freshness. Approximate nearest neighbor search may not always return the mathematically perfect top result, but it can return a very good result, fast enough for an application. Good systems expose knobs for recall, latency, memory, and update behavior. That matters because a chatbot, fraud detector, recommendation engine, and legal discovery tool may all need different compromises. Now, build a vector database workflow, step by step. Step 1. Collect the source items, such as documents, product descriptions, code snippets, or images. Step 2. Split large content into useful chunks, because one giant document vector is often too vague. Step 3. Run each chunk through the embedding model. Step 4. Store the vector together with metadata, like document ID, author, date, customer tier, language, or access permissions. Step 5. Create an index over those vectors. Step 6. When a query arrives, embed the query, apply metadata filters, search for nearest neighbors, and return the top matches. Step 7. Re-rank or post-process the results if quality matters. The important detail is that the vector alone is not enough. Production retrieval also needs chunking strategy, metadata, permissions, freshness, evaluation, and clear failure handling. Vector databases are especially useful in retrieval augmented generation, or RAG. A language model has broad general knowledge, but it may not know your private docs, latest policies, customer-specific data, or code-based details. A RAG system uses a vector database as external memory. The user asks a question. The system embeds the question. The vector database retrieves the most relevant chunks. Then the language model answers using those chunks as context. This pattern can power enterprise search, support assistance, research tools, shopping recommendations, image similarity search, duplicate detection, and semantic code search. But there is a trap. The vector database is not magic truth. It finds similar things. Similar does not always mean correct, current, authorized, or complete. The application still needs validation, source citations, permissions, and monitoring. So, what should you remember? A vector database is a database optimized for similarity search over embeddings. The embedding model turns meaning into coordinates. The vector database stores those coordinates, indexes them, filters them, and retrieves nearby items fast enough for real applications. It helps AI systems find relevant memory, instead of relying only on exact keywords or model training data. The best mental model is a map of meaning. Each item becomes a point, and useful answers are often found by looking nearby. The engineering challenge is choosing the right embedding model, chunking strategy, index settings, metadata filters, and evaluation loop. The takeaway: vector databases do not make AI intelligent by themselves, but they give AI a searchable memory that can make answers more relevant, grounded, and useful. Like, share, and subscribe for more simple AI explainers.